And kia ora and welcome to the Encryption webinar. And I'm going to hand it over to Tim to walk us through. Thanks, Tim.
Great. Thanks, Tracy. And yeah, kia ora tātou. Really good to see familiar faces there, and probably a few people who are had more experience teaching this than I have. So the idea of these is that I'll talk through some ideas, try and get across some of the big points and maybe some little points as well. But some of you may have experience and you can contribute ideas or things that you've found have worked, and certainly questions. We'll have a question time at the end, but if there's any pressing ones, maybe type into the chat, and if I completely miss it, then hopefully Tracy will jump in and wake me up and point it out. So, and speaking of the chat, if I could just ask you now, just type in roughly where you're at with encryption. Have you taught it lots of times? Is this the first time you'll be teaching it? Do you know a bit about it? Never seen it before? And just to give me an idea. Cool. And maybe Tracy, I can just check that. So hopefully my opening slide is there with the title on it. Cool. Great. Okay, so far everyone who's found the chat have popped in they've had a little experience. Isaac, welcome. First time, fantastic. Cool. So the way I'll do it is I mean, obviously in half an hour or 40 minutes, we're not going to get through what you would normally get through in what should be tens of hours of teaching and learning. But I'll try and emphasize some of the main points and see how you go. And yeah, it was a good point about computer security. So, and I'll try and remember to say a little bit about the difference between them. They obviously overlap massively. And put simply, encryption is about the nitty-gritty of the bits and bytes and the numbers and formulas and things that happen to make security possible. But security is much bigger because it involves humans and policies and all sorts of things, and it treats encryption as a given. Whereas today we're going to be looking at the actual encryption part. And what I've done is I've put together a document, which you're welcome to bring up now, and you should have permission to edit, to make suggestions in it anyway, or changes or something. And I've just put a few links so that when I'm talking about stuff, I can put the link in. If it's missing, just type in a comment saying, Tim, please, can you pop in the link to that thing that you showed us? And if you've got things that you've found really helpful, which is almost certainly the case, just pop in a comment or a note saying what they are as well, and so we can all share our knowledge. So I actually, maybe Tracy, you could paste that into the chat as well, so that people can easily access it. That's not too hard, or someone can. Should have lined it up for myself. Okay, so just going back. So for encryption, the challenge of it is for both storing and sending information. So that's really important. We're encrypting things that are stored on disk. We're encrypting things stored in cloud computer centers, things that are stored on your phone in case someone steals your phone. So lots of places where things are stored, but also that's sent or transmitted, particularly over the internet, but not just the internet, thinking of things like Bluetooth or radio mics. If someone's using a radio mic, before they used encryption for those, people used to record famous singers singing into a radio mic and put it on the internet, and you would find out that they weren't actually singing very well, that the audience was listening to a recording and so on. So anywhere where data is being transmitted and you don't want people to either receive it or to interfere with it. So, and we'll see that there's actually a whole lot of protocols in there. And so you've probably seen things like certificates for web pages and stuff like that to prove that the web page really is from where it's coming from. So encryption's got things like that, and voting, and we will look at passwords a bit. How do you store passwords so that people, can't steal them easily and so on. So it's all of those things. Now, the standard, again, planned for review in 2020, so looking forward to that. And it won't go over this in great detail, but basically, for Merit Achieved in Excellence, it's about knowing what the concept is, in this case, encryption, how it's implemented, how it's applied in real life, and the relevant mechanisms. And I'll probably spend quite a bit of time talking about mechanisms today, which is just the algorithms, and the maths and so on that's used to make them happen. And then for merit, explaining the impact of the concept, which requires understanding how it works so you can talk about its impact. And then key problems or issues. This is getting onto the edge of, well, what are the limits of particular methods and what are the issues around it? And the assessment specification, okay, for the standards is you could either do AI or encryption. And we'll be talking about AI in a week or two. Encryption is fairly mathematical, but it's also for some of your students it's nice and tidy. There's particular protocols, particular things that they can have a go at. AI can be a little bit more, about the implications and that sort of thing. And then the assessment spec for this year says that they will look at these things, and I'll try and touch on each of these, particularly the advanced encryption standard, which is the standard that lots and lots of stuff uses. So I'm talking to you at the moment through, if you bring up your settings for Zoom, it will say that you're using AES for this connection so that other people can't eavesdrop on it. Web pages use AES. It's just really widely used. Privacy, garage door openers. Actually, I did a bit of work on this since it came up this year. It's actually lots of interesting stuff going on with them, so we'll talk about those a bit. Secure hash algorithm, which I'll definitely talk about. The key exchange problem, absolutely fundamental, and use in healthcare. So you want to make sure your students sort of are aware of those things. They kind of range from very specific, like garage door openers, through to very general, such as privacy, but it's a good space to navigate. So big picture, standing back a bit, one of the foundations students will need is to really understand what binary digits are, because compression is measured in bits. So not compression, encryption is measured in bits, how many binary digits of encryption you have. And also remember that this is about just building excitement and interest, that encryption is something that's happening right under their noses all the time. And it's the thing that can make them feel secure, that people aren't reading their messages or keeping track of what they're doing. And there's a few sort of, I put game-changing or non-obvious concepts in there that I think can be quite exciting for students to realize that this is going on. So one is Kirchhoff's principle, which is simply that in any encryption system, you assume that the bad guy knows everything about how your encryption works. Okay, and they know everything except the secret key for unlocking your particular version. So they know that you're using AES, or they know that you're using HTTPS. They know exactly how HTTPS, the S stands for secure, works, how all the encryption in it works. The only thing they don't know is that number that is being used for your encryption today for this particular connection. And that number will be some number of bits. Okay, so typically about 128 bits, 256 bits. Sometimes we have more than that. And as long as they don't know that number, then how are they going to figure it out? So that's Kirchhoff's principle. The opposite of that is security by obscurity, where nobody knows how the algorithm works, and they've got to try and figure out what algorithm you're using for encryption. But the reality is most people don't even know they're using encryption, let alone that they're using the same algorithm as everyone else on the planet, for web browsing or something like that. The key exchange problem, when we all got onto Zoom, our computers all got the secret key for this conversation, and they exchanged it over the internet. And someone could have been watching our connections. One of your students could be eavesdropping on your Wi-Fi at the moment, but they still couldn't get that. They couldn't figure out what the key is and break into this conversation. How do you do that? Which is kind of a cool thing. Hashing, which means that we can store information in a way that we can prove that we know it without anyone else knowing what that information is. And that especially applies to passwords. You can prove that you know a password without anyone else knowing what your password is. But it can be used for lots of other cool stuff. And then again, just that idea that we use bits normally to measure how strong an encryption system is, although that often translates into time. So most of the systems we use can be broken, but typically will take about 1 billion years to break. And nobody cares if they break into the Zoom conversation in 1 billion years' time. The standard will probably have been revised by then. So we'll see. Um, I'll put up the slide, and I'll share these slides afterwards. These are some of the words that looking at the standard and so on, that your students should be able to just use in a sentence. So when they're writing about privacy or healthcare or anything like that, a lot of these ideas will come up, and not so much memorizing definitions, but just having played with these things, use them a bit so that they kind of know what they are and can use them accurately in a sentence. I won't go through them in detail at the moment. We'll touch on a lot of them, have already. I just want to step back a little bit briefly. So technically, encryption is a form of coding, and the word code is totally overused in computer science. It's often used to mean programming, but here we're talking about coding data, and we change the format of data. And there's 3 reasons that we change the format of the data that's being stored or sent. The first one is error control, where you take, I've just got an analogy, I've got a photo here, I've added some bits to it, some binary digits, so that if anything goes wrong when it's being sent through the internet or stored on my disk, I can probably put it right again. That's in a whole different standard. Not even sure if it comes up this year. I don't think so. Now, the other reason that we change the way that something's represented is encryption. Error control adds extra bits. Encryption keeps the same number of bits as you had in your original data file, but it scrambles them so that if someone got hold of it, it would make no sense to them. It would just look like random bits, random digits. And that's the main thing we're looking at today. But the other main reason data gets coded is compression, where the number of bits is reduced. We get rid of redundancy in the image or the file or whatever it is that's being stored, so that when it goes through the internet, it will go through faster. Pretty much all 3 of those things happen nearly all the time. Certainly for this Zoom session, we are using all 3 of these. If there's an error on the internet, it'll automatically fix the bits that you're receiving. It's being encrypted so people can't see this conversation, and it is being compressed so that I can get 24 frames of your amazing faces at a time, and rather than having one every 10 seconds or something like that. And most data being transmitted over the internet, this is happening. But encryption is pretty much a given now. In fact, websites, you can't really use them if it's not encrypted. And if you're using Wi-Fi, if you weren't encrypted, people would just read everything that you're doing on Wi-Fi and so on. And even on a cabled connection, you don't know where the other end, well, you might know where the other end of that cable is, but if someone's plugged into it and are watching all your data, then they will have intercepted it. And so that's not going to happen. And I thought I'd start by just thinking about what encryption have you used today. And, like I said, pretty much everything you do is encrypted. Normally, it's really good to brainstorm with your class about these things, but here's just a few examples that came to my mind. So obviously websites, the S is secure, uses encryption. Just logging in or unlocking something, unlocking your phone or whatever, that uses encryption. If you swipe a card to get in through a door, or a bank card, to pay for something, that's encrypted. Netflix, probably Spotify, just about any service where they don't want you to just capture all of their data, that will be encrypted. So it can only be decrypted to display to you, but not for you to store it. Cryptocurrency like Bitcoin is entirely, well, the name gives it away, it's entirely based on encryption. There's electronic voting, where it's allows you to have secrecy in your voting. Signing documents, really important. You can prove that it's you that approved the document, and yeah, legitimately. Think about even something as simple as traffic lights. You do not want people to break into traffic lights and start controlling them. That could actually cause havoc. And home security cameras, very much. If you've got a camera even at your front door, let alone if you had one inside for security, you obviously don't want people being able to decrypt that. I mentioned wireless mics, and of course the garage door opener, which we'll get into. So I don't know whether it's a good idea to start with this or not, but it's a very simple cipher. This is the Caesar cipher. It's a simple substitution cipher. It's totally useless. A level 1 student should be able to write a program that could break into this cipher. It only has 26 possible keys, and one of them is pretty useless anyway. But the idea of a Caesar cipher is that you just add a number to the letter that you are encrypting. And so, uh, for example, here the letter K, it's in the table, is encoded as the letter N, and it's just done by, in fact, typically by adding or subtracting 3 letters. That's the classic Caesar cipher, which is entirely security by obscurity. Um, if Certainly there's only 26 possible keys that you could have, how many letters you're adding. Um, so really emphasize to your students, this is not a real thing. But it does enable us to introduce a bit of terminology. So in particular, you've got the idea of ciphertext, which is the encrypted text, the plain text, which is the message that's being sent. And bear in mind, the plain text, like in our Zoom conversation, the plain text is the output of my video camera, right? That's the plain text. It's being encrypted into ciphertext, which is just some bits being sent to your computer and decrypted into plain text so you can see my face and my slides. So then there's a key, which is, in this case, how much they're offset. And of course, the number of different keys here, because there's only 26, you can represent the number 26 with 5 bits. And therefore, it's effectively 5 bits of security. Turns out 5 bits is not much at all. You could, again, write a program, try them all out, see which one contains reasonable text. But it then introduces this sort of assumption that we tend to make, and this is with transmitting data. This isn't, encryption is used for other things like cryptocurrency and passwords and things. But when people are sending data, and this is either by storing it on a disk or sending it through the internet, we have these characters, Alice and Bob, and for decades people have said that Alice is sending a message to Bob. Sometimes they use different names beginning with A and B. And we assume that they're being watched by Eve. So security people are absolute pessimists. They assume that the bad people know your algorithms, that they have perfect access to every piece of data that's being transmitted. And the only thing that Eve doesn't have is that key. So if I decide to use 21 as my key, then as long as Bob's got the number 21, then Bob can decode my message, and Eve can't, or at least Eve has to try and figure out which key I'm using. There's also this potential character called Mallory for the malicious attacker who is trying to feed things into our conversation. So Alice might send a nice, happy message to Bob, but Mallory intercepts it and feeds in a nasty message to Bob, or at least perhaps Alice is saying to the bank, give me $100, and Mallory changes that to $1,000 and ruins Alice's bank account or something like that. So there's also the possibility of someone inserting things in it. Where Alice and Bob are using the same key, that's called a symmetric key. And these days we normally use an asymmetric system, because symmetric means somehow Alice needs to get that value to Bob, and Alice can't send it to Bob through the internet because Eve is watching, and Eve would see that number going through. Now, the number itself, of course, is normally a much bigger number, typically 128 bits, 256 bits, sometimes even a couple of thousand bits. And just while we're on bits, actually, so on the field guide, probably in the past, your students have looked at how binary digits work. So if you've got an 8-bit number, then that will range from the number 0 to the number 255. If you're using an 8-bit key, then Eve only has to try out 256 different values, and one of them will be your key. Fraction of a second to do that. If, on the other hand, we go to 32-bit key, then actually, no, we'll go from an 8-bit key to a 9-bit key. And this is, again, a bit of a surprise for your students, probably. The number of possibilities doubles. So adding 1 bit to the key makes it theoretically twice as secure. There are twice as many values that Eve has to try out to try and crack your code. So every time we add 1 bit, twice as secure. A few caveats apply, but it's basically how it is. So when I go to 32 bits, it's ridiculous. This number here is about 4 billion. And so Eve would have to try out 4 billion different values to attack it. Now, that's still not many. Computers do billions of operations per second, so it might only be a matter of seconds, if not a fraction of a second, to go through all the possibilities. And by the way, and that's called a brute force attack, by the way, just trying out all possible keys. Um, and so with 128, and the field guide will let you put in 128. If we scroll up, you can see there's all 128 bits. It's not that many bits, but if you look at this number here, it's actually 3.4 with 38 zeros after it. And, because of course, every time we add a bit, it grows exponentially, the amount of things that are possible. And so that is just ridiculous. Even if you could do billions and billions of things per second, work that out, how many seconds it would take, and you're talking about millions, if not billions of years to try out all of the possibilities. And that's why 128-bit security is considered pretty good these days. There was a time when the US required everyone to have no more than 40-bit security. The government said if you're using more than 40 bits, you're a criminal. And that's just because at the time, a computer using 40 bits only had that many different possible codes, and that was enough that the government had half a chance of figuring it out with their computers, even though it was secure for most people. Right. Um, so, um, getting back to the Caesar cipher, which is again about 5 bits, which is like nothing. A brute force attack would simply say, well, let's try out a key of 1, and that's no good. Key of 2, that doesn't look interesting. Key of 3, it says kia ora koutou. So that tells me that I think I've got the key there. It wouldn't be done manually. It would be looking words up in dictionaries or something like that and say, look, there's a lot of words that seem to be proper words from a dictionary. And these days, of course, it wouldn't help if you're using a language like Te Reo Māori. It would soon figure out that that's a valid solution. But so brute force, just try out all the keys. You might be lucky and get it early on, but the probabilities are ridiculously low. Another type of attack is called a statistical attack. So here's the ciphertext, and all I've done is written a program that counted how often each letter occurs. J is the most common, Y is the second most common, and so on. So chances are, and it'd be interesting to ask your students what's the most common character in an English file of English text. The trick answer is that it's a space, and although the system has probably left a space as a space. So it's probably an E or a T. So J and Y probably represent E and T. Now I've only got 2 things to try out, and maybe I can figure it out pretty quickly. Another type of attack is called a known plaintext, where I know what you're sending, and so I can work out, and I know the ciphertext, and so I just got to work out the difference. So, for example, if you knew that I always began my messages with kia ora, then you would know that in this case, OME is kia ora. So the O must be a K. And in that case, it's very easy to work out the key. Again, Caesar cipher, I mean, you could do that in your head. With a lot of the others, it's still really, really hard. But generally, security people will assume that the encryption will have a known plaintext attack. They assume that the bad person kind of knows at least sometimes what you're transmitting, and that's not unusual because there will be protocols. If you're a bank, you'll probably begin with the word account balance or something like that if someone's downloading a bank statement or whatever. So you pretty much know how it's going to, what's going to be in it. They will probably fudge it to make sure that doesn't actually quite happen, but nevertheless, pessimist encryption people assume that it's a known plain text attack pretty readily. Oh, and just one other thing, of course, getting to the general computer security is the actually easiest way to get the key or the password is to ask the person for it. And that's the social engineering side. You send them an email and say, click here and I'll give you $1 million, but clicking there actually just goes in and digs out their passwords, or even log in here. Choose your own password, but I know that you'll choose the same one as you use for your bank account, that sort of stuff. And you just get people to give it to you. Which actually brings us to the garage door opener, because I'll go into a lot of detail about how to hack a garage door opener so you can open someone's garage door. That they mainly involve sitting outside the place for a couple of days. If I wanted to get inside a garage door, I would probably just hide around the corner. The moment they're going out, as the garage door goes down, I go and put my foot in the door and and then sneak in underneath it or something like that. So, there's always different kinds of attacks. But nevertheless, the encryption people, they're only worried about technically how do we stop people getting the key. So I just grabbed a few garage door openers off the internet. This one, it looks like it's got six. These are older ones. They have these dip switches in them, dual inline something or other switch. And you just have a pattern of up and down on these switches. It's a binary number, and it has to be the same inside the button as it is inside your door opener, and it knows to match them up. So this isn't really protection against hackers particularly, because, well, even with 8 bits or 10 bits, this one down here has got 20 bits. That's still only a million codes, and you could have something that cycled through a million codes in a couple of seconds or maybe a minute, and it would hit the right code pretty quickly. But what it does stop happening is your neighbor accidentally opening a garage door, right? So very early garage door openers had no security, and you'd press it, and every garage door in the neighborhood would go up. And so then you start putting a unique number on your one. And if it's 8 bits, there's only one chance in 256 that your number is the same as your neighbor. These days, well, later on, it got up to about 20 bits. So this door opener down the bottom is 20 bits. But someone could sit outside with a gadget. And in fact, I've put a link to a video in the notes from Veritasium. They do really good stuff. Actually, here they are. And basically, they got a child's toy that happens to transmit on the right frequency and reprogrammed it to run through all of the codes. And they could open a garage door in a few seconds because it would just run through every possible code and open a garage door. And so it's actually a really good video. I would use it with the class. Almost everything in it's relevant. It's got a little thing about how to make it a bit faster using De Bruijn sequences, which students don't need to know probably, but it's kind of interesting anyway. But most garage door openers these days don't do that. However, there will be a lot of old ones installed that do still do that, right? I mean, who's upgraded the garage door just because of the security concerns? It's mainly when it stops working that you get it upgraded. So they now use what's called a rolling code, which means every time you press the button, it then goes to a different code number. And it goes through a whole lot of randomly generated values. So each button press generates another one. The video goes into why that doesn't work either completely, because because you might have more than one garage door opener. And also you might press the button and it doesn't work. And so you press it again and it's on to the next code. And so there's always a range of several codes that it will allow. And there's a trick you can do where you basically, if someone presses the button, if you're lurking around the corner, you jam it so that it doesn't work on the garage door. Then they press it again, which will be the next code. And you've now got a code that the garage door hasn't seen before and will allow itself to open for. I'll let you watch the video. They explain it much better. But the thing is, do you really want to sit outside someone's house with a jamming thing, waiting for them to come home, when actually you could get a crowbar and yank the door open anyway, right? Yeah. Again, with security, the easiest thing is to ask them to open it for you. In other words, maybe they're coming home, the door opens, you quickly whip inside, and I don't know. I haven't done that, so your mileage may vary. I'm not recommending it. Okay. So that's garage door openers. Hashing is a topic which is a really big deal in encryption. So hashing is when we take some text or a number or whatever it is and just convert it to a number by putting it through a formula. It's called a hash formula. And so here's a super, again, not very good hash code, but the word cat, I could convert it to a number by saying, well, C is the third letter of the alphabet, A is the letter number 1, T is 20, add those numbers together, and so the hash of cat is 24. And so anytime we put the word cat through this formula, it will tell me the number 24. This is used, not the simple formula, but the idea of hashing is used all the time for passwords. So if cat was your password, it would be put through a hash formula, which everyone knows, Kirchhoff's principle, assume that everyone knows the formula. It will generate a number, in this case the 24, and it will store that. So your password isn't stored, it just stores the number 24. So when someone goes to log in, they type in cat, puts it through the formula and says, that's 24, that matches the one that's there. So if you want to hack someone's password, suppose you even got into the password files and found out that the hash of their password was 24, you have to find letters that add up to the number 24. Trivial in this case, you could easily do it. But the systems that are used in real life are called one-way hashing, and they tend to use exponents. So instead of doing 3 plus 1 plus 20, we've got 53 to the power of 3, 19 to the power of 1, 47 to the power of 20. And again, this isn't exactly what's used, but you can see that using that kind of thing, you suddenly end up with very large numbers, but also very similar words like cat and bat end up as very different numbers. And now, if if I manage to get your hashed number somehow, I need to figure out what values to put in here to get that number. And basically, it can only be done through brute force. You just got to try out lots and lots of values until you get there. And in other words, I would try all your passwords, possible passwords. If I try all possible passwords, well, I know what I'd start with, the word password and word let me in and 1 2 3 4 5 6 and QWERTY and so on, and see if it comes out at those. And then I'd write a program that goes through the entire dictionary. I mean, that's only a few million words. And see if any of those. And this is why we don't use words from the dictionary or names or anything like that for passwords. Then I go through all the words in the dictionary with the letter O replaced with the number 0, because lots of people do that. And so that wouldn't take long to do either. And then I try all the words in the dictionary with the number 1 at the end, because I know that people are required to add a number to it, and they probably add the number 1 at the end and so on. But after that, once we start getting into strange letters and so on, it's going to take a long time for me to try them all out. Now, there are several hash algorithms that are used. The one that's mentioned in the standard and one that's very widely used is called SHA-256. It's a secure hash algorithm. And it's a well-known algorithm. You can look up on Wikipedia the formula for it. It's moderately easy to calculate. It takes a wee while, and it's good that it takes a wee while, because if someone's calculating lots and lots of words, it will slow them down a bit. But the 256 means it generates a 256-bit number. So if you put the word cat into SHA-256, there's the binary number that it generates for cat. Okay. And so if cat was my password, that binary number would be stored. Normally, when you're looking online, it will show you the hexadecimal equivalent, because it's quicker to write down. Same number. So the word password hashes to 5E8848 and so on, right? Now, if I didn't know what your password was, I just got to try and find a word that hashes to that. A lot of work in doing that. There's way too many to figure out. But and this is a fun game to play with your students, if you break into someone's computer, into a website, and you manage to get hold of your password, and if you look online, there's websites like or You've Been Owned or something, which basically have a list of password files that have been for sale. Most of them are hash password files, which means that this is all that people are buying. Now, that first password, if you've got a good memory, you'll see that that is the hash of the word password. So you know straight away that if that was in the password file, that you know what that person's password is. The next couple are also words from just plain English words. Students might be able to guess them, put them into a hash. Actually, so I've put up a link to a hash function. You can type it in. So actually, one of those ones I think was let me in, if I got it right. Whoops, which has a hash of over here 1C8B. Oh, there it is. Okay, so that there was the password let me in, and so on. So, but that's how you would do that. There is such a thing as what's called a rainbow table, where you can put, if I copy that hash, I've put up a link to CrackStation, which offers to do this. You do have to prove you're not a robot. And there we go. So I gave it that one, and it said, oh, that just hashes, that's the hash of let me in. So that runs it backwards, and it will work if it's text. But one of my ones has got hashes and @ signs and all sorts of things in it. And there's no way that they would have put everything with hash signs and ats in their table that they're looking up. So probably you won't be able to figure out that one. Now, hash algorithms, secure hash algorithms can also be used for proof of knowledge. So I'd sometimes use this example. I don't know if you remember years ago when the referendum on cannabis was on, and Jacinda said, I've made up my mind, but I'm not going to tell anyone until after the voting because I don't want to influence it. And so what she could have done, and people went, oh, no, you're just going to tell us afterwards to go for the popular vote. She could have typed this text into SHA-256 and said, look, here's the hash of my decision, made it public before the referendum, and then afterwards she could prove that that was her decision by giving us this text. We'd put it into the hash and we'd know that that's what she had promised. And it's essentially, and there's also things like zero knowledge proofs, and it's not exactly how something like Bitcoin works, but it's the guts of it, is that you can prove that you have some information without telling people what the information is. Quite a few more complicated things going on with cryptocurrency, but hashing is really fundamental to proving knowledge without giving away information. Right. Oh, and I've mentioned correct station, so rainbow tables. Right. So we'll move on to AES, the Advanced Encryption System. So there used to be well, there is an encryption system called DES, something encryption. I can't remember what the D stands for, actually. It'd be on Wikipedia. And but basically, it got to the point where a standard computer had half a chance. Oh, defense, yeah, it was from the American Defense Department, might have been there. And anyway, it was marginal for being secure eventually as computers got faster, but AES is still very secure against all known computers, as far as we know. Anyway, lots of people are working on trying to crack it. Good people, the white hat hackers as well as the black hat hackers. Oh, data encryption standard. Thank you. And the so AES is just a bigger, better version of it, basically. So it uses keys ranging from 128 to 256 bits. Very hard to guess them. And there's a diagram here. It's explained in more detail on Wikipedia. Don't think your students probably need to know all the details, but it's pretty straightforward what it does. It goes through 3 phases. So first of all, every byte is substituted with another value. So it uses the key to decide what to substitute that byte with. Actually, very much like the Caesar cipher, right? But not moving everything by the same amount, but swapping a particular pattern for another pattern. Then it shifts the rows so that all of the bytes in your data get shifted around into different rows. And then it mixes them within columns too. So you imagine that you've got a 2-dimensional list of bytes. The rows are shuffled, the columns are shuffled, and then it adds a number to it as well. And it has this idea of rounds, which is just, it does that multiple times. I think it's typically about 10 to 16 times. At different levels of encryption, we'll do it more and more times. Now, every time, so it takes the data out of that, puts it back in again, does all the shuffling again, then puts it in again and shuffles it again, about 10 or 15 times. Every time you put it through another round, it basically multiplies how difficult it is to be able to crack it. So you end up with a really, really muddled code at the end. But as long as you've got the key, you're able to run it backwards through the system. And with even 128 bits, it would take billions of years on the fastest computers we have to try out all the possibilities. You might be lucky, you might get there halfway. It might only take you half of billions of years to get there. But that's how AES works. But more importantly, I think students can investigate it. So for Zoom, you could look, if you look at your settings right now under statistics, it says that it's using AES 256, at least it is for me. Okay. Well, I guess it'll have to be for you, otherwise you can't decrypt it, what I'm sending to. And likewise on web browsers, I was trying to buy a kettle for my in-laws and had a look at the security on this, and it uses AES 256 as well for farmers, right? So it's really good. I could do my browsing of kettles in farmers, and nobody else would know that I was trying to buy a kettle, which is good. Well, now you all know, actually. Yeah. Cool. So Um, but that level of security is just applied to everyday transactions, everything that you're looking at online. And a lot of students would go, I don't care what people, about people seeing what I am looking at online, but it's also preventing Mallory from dropping stuff in as well, right? So it's used for Wi-Fi if you're using any reasonable Wi-Fi standard. It's AES, WhatsApp, Signal if you're doing anything a bit secretive. Um, Cloud storage often uses it, and one of the important things is end-to-end encryption, which is probably something for your students to be aware of. If you save something on cloud storage, depending on who it is, like Dropbox or Google Drive or whatever, if your computer encrypts it and it's sent to them encrypted and it's stored encrypted on their system and it's only decrypted by my computer, then Google or Dropbox or whoever it is never have access to my file. They know that I've got a file and they know I've been editing it a lot. But if, in particular, American law enforcement come to them and say, we demand you show us Tim Bell's files, they'll say, well, here's his encrypted files, but he never sent us unencrypted files. So, sorry, I can't tell you if he's been buying kettles or not. So that's cloud storage, online banking. It's sort of an obvious thing where you want security. VPNs, virtual private networks, because if the whole reason people use VPNs is to be able to sort of get around the system. It's no good if people know exactly what you're sending through them, and lots more. Now, I think probably the main other theme I just want to quickly go through is the key distribution problem. How does Alice choose a key and get it to Bob? And there's a really clever way of doing this, and it's used all over the place. So it's called a Diffie-Hellman algorithm. There's a few algorithms thrown together, but if you look at Chrome and go to the developer tools for a particular website, just in here, you see ECDHE. The DH means it's a Diffie-Hellman algorithm. Which is how one website agrees with another on what the secret key is without the person in the middle. They can see everything. Eve can see everything going back and forth, but never knows what that key ends up as. So we'll have a look at how that could possibly happen. If you get the video at the start of the computer science field guide. So here we go. One of my students did a short video which shows the key exchange problem, in which Alice is inviting Bob to a party, but she doesn't want Eve to come to the party and know where the party is. And they keep on saying how mean that is, but apparently Eve can't be trusted at the party. So anyway, they're exchanging information right in front of Eve, using high school lockers to lock away the information. So that sort of introduces the key exchange problem. It's one way of doing it anyway. Now, what the key exchange problem is, it's you can actually use it. What normally happens is you use Diffie-Hellman to swap the keys, and then it switches to AES, right? For the actual data exchange. So because key exchange Diffie-Hellman is slow, and you don't want to do it for every bit of data that you're sending through, but you use it to agree on a key with the computer at the other end. When I say your computer has done it, you probably didn't even know that our computers were talking to each other about this. And then you can go ahead with that key. This cartoon kind of illustrates it as well. So you have the idea of a public key and a private key. And so a public key means anyone can lock away the information that you want. And there's a private key that only you can access. So you let anyone sort of lock up this information, but only you can read it, even though anyone knows how to lock it up. That's an asymmetric cipher or a public key system. Now, there's several different protocols around there, but what I'll do is I'll illustrate the Diffie-Hellman one, because it really is used in lots of systems, and obviously when you're talking about implications and so on, everything that uses it has implications for them working. So one of the analogies that's sometimes used might be confusing, but I'll try running through it anyway. I'll do it with numbers in a minute, which might be more or less confusing than this. Is you imagine that Alice and Bob had to agree on a paint color. So the paint color is their secret key. and it's completely in public, so people can see all of the exchanges between them. So Alice and Bob, they just publicly say, look, let's start with this color yellow. And everyone, including Eve, knows that there's a color yellow. And then Alice and Bob each secretly choose a color that nobody else in the world knows. Only Alice knows that she's chosen orange. Only Bob knows that he's chosen green. Then they both mix those colors together, um, and they end up with a different color. Then they publicly swap those colors with each other, right? So everyone in the world knows that the mixture of yellow with Alice's color is orange, but we assume that nobody knows how to work that backwards, that if you're given a mixed up color, then you can't work out what the two colors are that made it. Because there could be, well, anyway, we're just assuming that. In reality, this is mathematics that can't be run backwards. If I give you two numbers that have been into a formula and you know the output, you can't figure out what the numbers were that went in. So now Alice and Bob have each other's mixed colors. Neither of them knows each other's secret colors. Then Alice adds her secret color to Bob's mixed color, which gives her this kind of brown. But Bob adds his secret color to Alice's mixed color, which will give him exactly the same color, right? Okay, so that color is a mixture of the yellow, the orange, and their two colors, secret colors. So neither of them have told each other their secret colors, but they both now have that common brown secret that nobody else in the world can figure out. Right? Let's do it with numbers. Maybe it's easier, maybe it's not. This uses modular arithmetic, which your students might not be familiar with. I think it might come up in the curriculum a wee bit. Actually, feel free to type into the chat if you think your students know modulo. It's just clock arithmetic. It's just the idea that if it's 10 o'clock and you add 4 hours, then it's 2 o'clock. If it's 10 o'clock and you add 6 hours, then it's 4. Oh, did I get it right? I'm confusing myself. If it's 10 o'clock and you add 12 hours, it's 10 o'clock. If it's 10 o'clock and you add 1 hour, it's 11 o'clock, right? So it's whenever you get round to 12, you reset to 0. Except I'd illustrate it with modulo 10, which is whenever you get round to 0, you reset. So on the clock I've shown you here, 8 plus 3 will give you 1, right? Three clicks past 8 is 1. And so that's all that modular arithmetic is. Computers are good at it. There's a modulo operator in most programming languages, including Scratch and so on. So we'll skip that. The other thing that students need to know is exponents, which is just 5 to the power of 2 is 5 times 5. But 2 to the power of 5 is 2 times 2 times 2, 5 times, okay? So it just means multiply this number by itself that number of times. So that's what an exponent is. It comes up in lots of areas of computer science too, so it's worth them knowing. It's pretty straightforward what it is. I've just actually grabbed this from Wikipedia. They've got a great explanation, but I'll feed it to you slightly slowly. So it's exactly the same as what was happening with the paints. This is the Diffie-Hellman algorithm, except now it's with numbers and modular arithmetic. So somehow Alice and Bob come up with these two numbers, 23 and 5. They can publicly agree on them. They don't really know. Their computers generate some random numbers and just swap them public. Eve knows those two numbers as well. Okay. But then Alice's computer makes up another random number, in this case 4, which doesn't seem very random to me, but that's all right. And Bob's computer makes up a random number as well. And then Alice combines her secret key, that number 4, using the public numbers, P and G, which are 23 and 5, using this formula here. So G to the power of 4 modulo P, which is 23, okay, which just happens to be the number 4. Students should be able to work that out. I mean, 5 to the power of 4 is just 5 times 5 times 5 times 5. Modulo 23 means it's basically the remainder if you divide it by 23. Or you can just plug it into a programming language and it'll tell you what it is. Meanwhile, Bob takes those public numbers, P and G, and puts his secret key in, the 3, so 5 to the power of 3, and that formula gives him the number 10. Then Alice and Bob swap those numbers, the 10 and the 4. So Alice has got Bob's 10, Bob has got her 4. Nobody knows how to run these formulas backwards. Now, in real life, we're not working with single-digit numbers. We're working with 128-bit numbers or 256-bit numbers, right? So there's no way you can try out all 256-bit numbers to figure out what was going on there. But then Alice simply puts her one through this formula. Sorry, she puts Bob's combined number through this formula to get 18. Bob puts Alice's combined number through the formula, and he will also end up with 18. And so now they both have the number 18. Eve has no way of getting that number, and um, and Bob never knew that Alice came up with the number 4 as her secret one, but Bob does know that his key combined with hers gives you the number 18, and Alice knows that her key combined with his gives you the number 18. So they've both got the number 18, but anyone watching all of their swaps has no way of figuring it out. So now they have a key, and they can use that key for an AES, Advanced Encryption Standard exchange, because AES is much faster. Because Diffie-Hellman, you have to go back and forth about 3 times to just to get a simple thing through. But now that you've got that number through, you can just use that for AES to do your encryption. And yeah, so here are the formulas. So it's just G to the A mod B, G to the B mod P. And down here, so basically Alice will end up with G to the B to the power of A, and Bob ends up with G to the power of A to the power of B. They happen to give you the same number when it's mod P. And so that's how they end up with the same number. And then they've got symmetric keys that they can exchange. Right. Now, that's pretty much all the encryption I was going to talk about. For this year, it's going to talk about healthcare, apparently. And I was sort of thinking about, what comes up in healthcare. Obviously, patient data privacy. Doctors are storing your records; they will be encrypted. Data breach mitigation. So you remember Waikato had a whole lot of data stolen and held to ransom. If that data that was stolen had been encrypted, they probably weren't encrypting properly. But if it had been encrypted, then you could just say, knock yourselves out, make it public if you want. It's encrypted, 256B bit key. A couple of billion years, everyone will know all about the Waikato patient's personal history. And so, it's obviously really important there if it's done right. Secure data sharing, and I go to one doctor and they say, "Oh, Tim's got this illness," and they send it to my doctor and so on. And here's, or like blood test results, for example. I get a blood test result that says I have a very embarrassing disease or whatever. That gets sent to my doctor. I don't really want an eavesdropper to figure that out. And then regulation compliance, just simply, obviously the law will say if you are dealing with such sensitive data as people's health, then you must not make that available. And of course, there's a lot of interest in it. Your life insurance company would love to get that data. If they think you haven't got much time on this planet, they might up your premium or something like that. So you may have other ideas, but the garage door opener I thought was great because it's got actual numbers that you can muck around with and do stuff with. This, it's probably a bit more arm wavy, but nevertheless, absolutely crucial how people are doing that. And there'll be anything that happens on the internet uses encryption. So any health stuff on the internet will do that. But think about, gadgets like blood pressure machines and home test units and, the kind of scans and things that people will be doing in the future on themselves. Right. Endless other things to talk about. One thing, it does mention the future, and I thought I'd just quickly mention quantum computing. Quantum computing's in its infancy, but there are quantum algorithms that don't quite work at the moment, but would weaken or break some of our important methods. AES is safe against all the known quantum computing that we have at the moment, but who knows? But the good thing is quantum computing will create new methods as well. And so if it becomes widely used, then people can then get quantum chips in their own computers, which seems far-fetched, but it's not that big a deal if it's possible, and have much better encryption anyway. Right, I will stop there. And discussion ideas. What have we missed? What should we cover? What did I go over too slowly, too fast?
Kia ora, Tim. I am going to just stop recording there, and then we'll have a kōrero and karakia after.
Mm.